Hello and welcome to C++ Weekly. I'm your host, Jason Turner, available for code reviews, contracting, and training. This is another PMR and allocators episode done in collaboration with Bloomberg, and as always, the views, ideas, and opinions expressed are entirely my own. Now, if you're paying attention to the last couple of episodes, I suggested that deeply nested data structures are really the kinds of things that could really benefit from many of these allocation strategies and things like winking out data and some of the more obscure things that we can do with allocators. And I really started thinking about this, and I thought about JSON files. Now, talk about things that are deeply nested. You've got maps of arrays of strings with maps in them, with arrays inside of those, and these things can actually get really complicated. And so I went looking for some ideas for how I might be able to prove that this is a good use case for allocators for the sake of these videos. It seemed like an outstanding way to wrap this up. And then I learned that Boost JSON is going to be part of Boost 1.75. And I went looking at Boost JSON because it advertises that it has full allocator support. So I thought, well, maybe this would be a good one to play with. I was also looking at nlowman JSON, which is very popular. And it turns out that Boost JSON actually publishes their own benchmarks. And they've got these pool ones noted. And they show somewhere on the order of 3 times the performance difference and 2 times the performance difference for using pool allocators with Rapid JSON and Boost JSON. So I thought, well, QED. My work is done here. End of episode. But not really, of course. There's more to talk about here. The first to note is that these say pool allocators. That's really not correct. These are both using monotonic style allocators for these benchmarks. The Rapid JSON allocator that it provides by default is a pool allocator on top of a monotonic allocator, which is backward from the thing that we were talking about previously. But it gives you, well, outstanding performance in their use case, but you have to keep in mind that if you're doing a bunch of manipulation of your JSON DOM with either the Boost one with a monotonic backing or the Rapid JSON with its monotonic backing, your memory will continue to grow because these allocators don't do anything when they free. The other thing that's worth noting is that for the, I'm going to circle the defaults. This is the default, and this is the default, and this is the default. So with Rapid JSON, their pool allocator is the default way that it does things. With Boost, so you have to jump through hoops if you want to make Rapid JSON slower, and you have to jump through hoops if you want to make Boost JSON faster. So looking at the default performance of these things, well, there's a reason why it's called Rapid JSON. And of course, there's a bunch of other tests here, and you can see the differences between MSVC, GCC, and Clang here as much as you want to. This is just one of the JSON file example benchmarks. So I wanted to see if I could make the very popular nlowman one work with allocators. And I wanted to see what our options were for Boost JSON and Rapid JSON. That's going to bring us back to this PMR benchmark stuff that we were looking at from the last episode about PMR. So the default for Boost JSON looks kind of like this. We create a stream parser and an error code to store the results in. And then we write our input string into the parser and then have to do some sort of finish and release here on each iteration. At least that's the examples that are from the official Boost JSON test suite. And now, if you want to use PMR with it, you actually have to use Boost JSON, as far as I can tell, in standalone mode. If you use it as part of Boost, then it wants you to use the Boost version of these things. If you use it in standalone mode, then you can use the C++ version of these things. So in this one, I have created my own monotonic buffer resource. I'm not giving it a default size. I'm just going to let it grow as it needs to. And then I create a polymorphic allocator from this. And this is a wink out version. So we're going to have to talk about this in a moment. That's the wink out version. And then I've got one that doesn't do the winking out. Now, if you don't know what winking out is, you're going to have to go back to the previous episode. I'm not going to cover that right now. So I've got Boost JSON, and I have this one commented out. Now, we'll discuss this later. Rapid JSON supports allocators. As I said earlier, you can choose which allocator you want, and you have to jump through some extra hoops to actually slow it down. So the default rapid JSON is very simple. It's like this. We just create a rapid JSON document. We ask it to parse the input. And if we want to use their CRT allocator, which is the one that uses the common runtime effectively, it's the one that uses new and delete or malloc and free, then we have to create the CRT allocator and create a generic document and pass in the allocator to it, and then ask it to parse it. Now, if we want to pass a PMR allocator to it, which is the way that we can then play with all of these examples that we've already been talking about over the last several episodes here, then we need to pass it a polymorphic allocator. Now, the problem is we can't just pass it a polymorphic allocator because its allocators are not C++ standard compliant allocators. Its allocators have their own definition. So I created an adapter for using PMR with it. And this is my rapid JSON PMR allocator. And it has this upstream resource behavior because we want to be able to just pass it new and delete resource and that kind of thing. And then, yes, it does need free. Now, note how I said before that by default, their allocator is more of a monotonic style allocator because it's free actually does nothing. And you can see that in the fact that they have chosen to make free a static function. So this means now that my adapter has to do quite a bit more extra work because when I allocate something, I actually have to store with that allocation the length of the allocation and a pointer back to myself. And then I can further realloc. I just allocate more memory and I copy it in because allocators don't have any concept of realloc. And then for free, I actually have to get the pointer that they passed me, subtract off the amount of padding that I added for my own purposes, get a pointer to the object that is my allocator that's at the start of that buffer, and the original allocated size, and then pass those things into my free pointer function here, which calls the upstream deallocate. So these things all ultimately rely on the upstream allocate and the upstream deallocate. That was a bit of a pain, but I got it working. And it actually ended up making some very interesting numbers. So it's important to note you actually have to run this thing from the data folder so that it can find the JSON files. It's going to have to be a little bit smaller font than I prefer so that we can actually fit everything on the screen here. But what we've got is our JSON performance test running, and we're starting with the Boost JSON default parse. So this is one that is using effectively the new delete resource, and it's able to do 520 megabytes per second. And if I do this monotonic parse, then it's able to do 910 megabytes per second. That's almost twice as fast. So it doesn't quite match the benchmarks that we were looking at on the website for Boost JSON, but different environments. I don't know. And we see this kind of behavior consistently. So if we've got the default thing versus the monotonic one, then we're getting somewhere around, actually, yeah, a little bit less than twice as fast. And I'm only doing a handful of these different performance tests. And then if we compare it to RapidJSON with its default, which, like I said, is already a custom allocator that is similar to the monotonic one, 920 megs per second. If we do the CRT parse, now that's the one where we're using their provided new and delete resource effectively, 638 megabytes per second. If we use the PMR one, 614 megabytes per second. So slightly slower, and we're seeing some of this overhead of where I have to keep track of where things have been allocated in memory. And then getting to the monotonic PMR resource here, then we're at 822 megs per second. So we're getting pretty close to what their custom built allocator can give them. But it's obvious. I mean, the implications here are very clear. It's for the parsing behavior, we can get somewhere on the order of 2 to 3 times faster, depending on what exactly your setup is. And that's huge, right? I mean, that's absolutely amazing. But it doesn't even take into account the differences in access behavior. So if you know that all of these things are being allocated in the same contiguous chunk of memory, then your accesses are going to be that much faster as well, again, which is pretty cool. So yeah, we see this kind of thing over and over again here for how the performance works out between these different allocators and options. Now, I'm using the monotonic here, and if I use the pool monotonic that we discussed in the last episode, that gets a little bit slower. But again, the pool monotonic has this huge advantage that we can actually modify the data in there without continuing to grow. We can add and remove things from the DOM. So if you're doing a lot of data manipulation, then you probably want to put in one of these pool monotonic combination things for any of these JSON parsers. I didn't make any benchmarks yet that actually compare what manipulations look like, because honestly, I don't really know what kind of manipulations one would do on a JSON document, but it's something that you need to keep in mind. Your usage patterns will hugely affect the way you do this. And as we saw in the last episode, fortunately with PMR, it's like crazy easy to try different combinations of allocators and different tools to see what different usage patterns with our code can actually result in better performance. But we need to talk about these wink out ones. So all of these JSON parsers, the Boost JSON and the Rapid JSON, say that they support custom allocators. But maybe not everything that they are allocating is actually using the custom allocator. So let's go ahead and run one of these. So I just ran just the one, Google Summer of Code, PMR, monotonic parse. Now I'm going to run this through Valgrind. I will zoom this a little bit again. And I'm just going to run Valgrind in its normal mode, which checks for memory leaks and memory accesses that are incorrect. And we see that we have absolutely no memory leaked here at the end of this program executing. Now we're going to run this with the PMR monotonic wink out parse. And now we see that we had 589K definitely lost. That means that there is data that is being allocated inside of this JSON parser that is not using the allocator that I passed to it. And therefore, because the destructors are not properly being called, we're getting this loss of memory. Now, it is interesting to note that this is a pretty significant difference. Right here is the difference we're looking at between winking out and not, because these deeply nested data structures, if it can just go poof and let the memory go away, safely and correctly, then that's awesome. But if you are doing anything inside of your data structure that is not using the passed-in allocator, then it's going to cause a memory leak. And in fact, we can see the same thing with rapid JSON. It's considerably smaller. It's only 4 bytes that get lost. But if we take out the wink out, then we get 0 bytes lost. So it's also doing something that's outside of the allocator that we passed into it, something that needs to be properly cleaned up. So that brings us now to the end of our story, and the homework assignment for you, if you choose to accept it, is trying to use the in-Loman JSON with PMR allocators. So in this code, I am not doing anything fancy at all. All I'm saying is that I want you to use a standard map, a standard vector, and a PMR string with my polymorphic allocator template right here. This is how it is intended to be used with a custom allocator. Now, unfortunately, I have to do standard PMR string because it doesn't forward the polymorphic allocator to the string that's passed in. So I have to specify I want the PMR string. And but otherwise, I am supposed to specify standard map and standard vector because it passes the allocator as one of the template parameters, the second template parameter, third template parameter in the case of standard map. So there's a little bit of disconnection here. But if I do this and I attempt to recompile, I'm going to get a very interesting and large set of errors. And what it comes down to here is this no matching function call for an invoke of the allocator, blah, 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 that takes a polymorphic allocator. So basically, none of the constructors for this JSON parser properly take an allocator for their final parameter. You have to go back 4 episodes in my PMR series to see what that means and how you create your own allocator aware types. But this is not properly an allocator aware type. It behaves as one, but then doesn't actually take an allocator object to actually use for its stateful allocation. So if you want a homework assignment, what you need to do is go in and you can grab this from my C++ Weekly repository and try to get this code right here compiling, lines 98 through 106 at the time of this being built, and tell me once you get it all working. Now I will say I got it all compiling. I did. And I have that in my own private repository. But it actually shows a fairly significant performance regression. And I believe that what is happening is that there is some data that is being created outside of the allocator and then having to be copied into the custom allocator fairly regularly. And that's going to cause a big performance problem. So the takeaways here are absolutely 100% custom allocation, huge, huge, huge win for something like JSON. I'm just going to go back to this chart so you can see this chart. Huge win for custom allocation for something like JSON. There's absolutely no question that you should be pursuing custom allocators for your code if you have performance problems. Make your types properly allocator aware. You've already seen that there can be a gigantic performance gain here, but for it to really be useful and composable like we want it to be, make your types properly allocator aware. I want to know that if I take your type and I put it in a PMR map, that it's going to properly pass the allocator down into your type, for example. So make sure you do that. Go back to the previous episodes on that. We can't understate how big of a win it is here for something like JSON. I mentioned winking out a few times here. This is an advanced topic. If you want to actually use this thing, you need to know the exact implications of what you're trying to do when you're just letting the memory go. You need to make sure that all of the things inside that are contained in your allocator and that this is safe and you don't have destructors with side effects that you care about. And don't forget to do your homework. Do your homework. Go ahead and try to make Lohan JSON parser fully compliant and able to work with polymorphic allocators and PMR, and then bring that back here, and we'll see just what kind of performance gains are possible once it is plumbed through the whole system. So thanks for watching this episode on PMR, and be sure to subscribe.